Greetings. Here's our next Coriolis problem, and if you look at it, the format looks a little different compared to the other problems we've seen. Well, there's a reason for this. This is a former exam problem, and this is the exam statement. Okay? And why do we have this? Is because every single time I put this problem on an exam, it has been an unmitigated disaster. I won't put this one on an exam anymore because it's now part of the lecture series. So, what do you see here? Well, here's a link, and if you'll compare them, this looks a lot like Coriolis, because here's point B. Point B is touching this thing everywhere. This thing is touching this link here, only at one spot. So it looks really Coriolis. Yet, anytime anybody tries to do this, it blows up. So let's look how we should do this problem. All right, and we have, you'll note there's various geometry stuff here. So this problem's a little interesting, but let's just see what we get. So we have velocity here coming up at 2 meters per second, and this one's accelerating up at 3. And then the question, of course, is determine the omega and alpha of this length AB here. So we have to go from here up to there, and we're going to have to make a jump from this B on this link to B on that link. So it looks really Coriolis. But let's start looking into it. So here's the work for this thing. So the velocity part's fairly straightforward. So let's see what we can see. If we go from here to here to get, this is the link 3. It's touched in one spot. This is the link 2. It's touched everywhere. All right. So to get B on link 3, it's obviously omega A, B, omega for this, cross R from A to B. Nothing new here. And if you multiply all that out, okay, we got omega AB cross R. So the length is 0.027 meters. This is at 45, so it's minus sign. It would be depending on which. If I take the 45 here, I get cos 45 negative x and minus cos sine 45 y. This is measuring the angle from there. Flips it. Okay, whichever way works for you. So we have this cross product, and what else do we know? Well, if we look at, we have a lot of information right here. The velocity of this thing is coming up at 2 meters per second. Okay, well, that means the velocity of this point, based on link 2, is going to be coming up at 2 meters per second. If this thing is going up at 2 meters per second, you know darn well that this thing in the slot's going up at 2 meters per second. All right, so when you multiply all this stuff out, then there's going to be, relative to ground here, I'm taking that, this is going to have motion in the slot, so there's going to be something x, plus definitely 2y. AB is relative to ground, so that's all good. Solve it. You have 2 equations and 2 unknowns. Use the y term to solve for omega AB, and then solve for the x. And that's what we have here. So here's omega AB based on the y term, and we weren't asked for Vx. I don't know if, I didn't even bother to compute it. That's fine, nothing wrong with that. So we got this term, we needed it. All right, so let's move on to the acceleration story. All right, just a second, getting my notes lined up. So we're going to get, we need to get acceleration of B on length 3. So if I was attacking this problem, here's what I'd do. I would note that at the end of the day, what we're going to find is that B on 3, because of what is happening to this slot, this is accelerating up at 3 meters per second squared. Therefore, B, no matter how you cut it, has to be going at 3 meters per second squared, or it's coming out of the slot, which is a completely separate problem. And then there's going to be some x component. All right. What you're noticing here is I'm not doing any Coriolis here to do this problem at all. Okay? I'm just looking at this thing like going, well, relative to ground, I know this is going to come up at 3 meters per second squared. It's going to do something in x. I'll figure it out if I need to. But I don't need to. What am I doing here? The whole point is if I set this side up, I have one unknown, and then I can solve for it. And then my problem's done. So let's look at this. Going from here to here, this would be alpha cross r minus omega squared r. And that's what this says. Okay, I can go from here to here doing all my conventional stuff we've done in the past. It's absolutely accurate. All right, and that leaves me with relative to y. I can take the y component from this side, equate it to 1, bam, I get alpha AB. Problem's finished. And that's what I did. We have it. So, why didn't I use Coriolis? And the fact of the matter is, as anybody goes to do Coriolis, they usually get themselves so confused they can't even do the problem. All right? You just have to understand Coriolis. So let's look at the Coriolis solution to this problem. It's right here. Don't want to go there yet. So Coriolis would say, go to AB, B on 2. Okay, where's 2? Right here. It's coming up at 3 meters per second squared. Then it would say, add in the Coriolis term. And this just drives students crazy. Here's the problem. Omega 2, this is the thing touched everywhere. Is this rotating? Not a bit. Omega 2 is 0. This whole term flushes out. All right? And then what you're left with is how does 3 move to 2 for somebody observing it? Well, let's just put it this way. If you are sitting on this link, what would you see this slot doing? Moving along the x. So 3y plus AB 3 along the x. That's what I have right here. That is what Coriolis gives us. This piece right there. What we looked and did right away. This problem, because this is not spinning, there is no Coriolis to worry about. We can just do it directly. And that's what I've done. All right, so we're going to move on. We've got, I think, 2 more problems I'm going to be doing. I'm just going to check here. 1. Yep. 2 more problems, and then that will finish up our Coriolis story. So I'll start another video for that one. Catch you in a moment.